Welcome to lesson 2.2, conditional statements. So the big idea of this lesson is that conditional statements are the basics, the basis of logical mathematical thinking. So conditional statements you can think of as that foundation that we base logical mathematical thinking around. You'll also see conditional statements come up in many different sciences. So in mathematics, our definition of a statement is a sentence that is either true or false, but not both. So to be a statement, it's a sentence that is either true or false, but not both. And then we have what are considered compound statements. And compound statements are a sentence that combines two or more statements with some type of connective term, such as and, or most traditionally in mathematics, if, comma, then, or if, dot, dot, then. So basically connected with a conjunction. So compound statements are sentences that combine two or more individual statements with some type of if, then, and, or some other type of conjunction. So then that brings us to our big idea, which is conditional statements. And conditional statements are compound statements that are written in if, comma, then form. So our if-then format. So conditional statements are always in an if-then format, and they are compound statements. So examples of conditional statements. If the light is red, then you must stop. If you live in Fond du Lac, then you live in Wisconsin. A figure is a polygon if it is a triangle. So right away, you're wondering, well, where's the word then? It's not in that sentence. But because we could rewrite this statement as if a figure is a polygon, then it is a triangle, it would be considered a conditional statement. It is just written currently in an inverse type form, where we're flipping the order. So it's written as a figure is a polygon if it is a triangle. But we can think of that sentence as our conditional statement. If a figure is a polygon, then it is a triangle. And our next one, you can get your driver's license if you pass the test. So we could rewrite that as our if-then conditional statement. If you pass the test, then you can get your driver's license. So in these conditional statements, we have our two different parts, the antecedent and the consequent. And I know for many of you that enjoy algebra, you're probably wondering at this point, when did I join another language arts course with all these definitions? But again, a lot of our geometry is based around these definitions, so bear with me. But antecedent is the statement that follows the if. So it's also the hypothesis of our conditional statement. So antecedent is the same thing as the hypothesis, and it follows the if. And then we have the consequent, which is the statement that often follows the then part, depending on how it's written, which we'll look at. So it's the statement that often follows the then of the if-then statement, and it is also known as the conclusion of our conditional statement. So every conditional statement has an antecedent and a consequent, or we could think of that as a hypothesis and a conclusion. So in example 1, our 3 parts, A, B, and C, they want us to write the antecedent and the consequent of the following conditional statements, or our hypothesis and conclusions. So the if is followed by 2 unique lines intersect. So the if 2 unique lines intersect would be our antecedent, then they intersect at exactly 1 point. So then they intersect at exactly 1 point would be our consequent. In B, we have the statement, if 2 points are distinct, then there is exactly 1 line that contains the 2 points. So our antecedent follows the if. So 2 points are distinct would be our antecedent. And our consequent, or the conclusion, would be there is exactly 1 line that contains the 2 points. So the hypothesis, if we have 2 distinct points, the conclusion is there's exactly 1 line that contains the 2 points. And then in C, it's written as you can get your driver's license if you pass the test. And as we explored earlier, we could rewrite that as if you pass the test, then you can get your driver's license. So in this case, the consequent doesn't follow the word then because it's not there. The antecedent follows the if you pass the test. And we think to ourselves, if you pass the test, then you can get your driver's license. So you can get your driver's license would be our conclusion or consequent. In example 2, it asks us to rewrite the following statements as a conditional statement. So statement A says all segments are convex sets. So we could say if there are segments, then the set is convex. Because in this case, all is an absolute. So in all cases, segments are convex sets. So if there are segments, then the set is convex would be one way to rewrite that as a conditional statement. In B, the slope of the line containing 2 points is the change in the y coordinates divided by the change in the x coordinates. So that statement or sentence is basically the definition of slope. We could rewrite that as the conditional statement. If there is a line containing 2 points, then the slope is the change in the y coordinates divided by the change in the x coordinates. Then example 3 asks us to rewrite the following statements using symbols. So we can also call this process abbreviating conditionals. So if you're ever exposed or hear the term abbreviating conditionals, that means that you are rewriting the following statement using symbols. So you're abbreviating conditionals, abbreviating the wording using symbols mathematically. So in A, it says, if I move my queen here, you will take my rook. Or you will take it with your rook. Sorry. So if I move my queen here, you will take it with your rook. Obviously a chess scenario. So we can abbreviate these different parts with symbols or letters. And in this case, I can think of this as if I wanted to rewrite this, I could write if Q, then R. And that's a traditional way to represent a conditional. If Q, comma, then R. So we're abbreviating it with the term if and then Q over here represents if I move my queen here, and R is you will take it with your rook. So over here I gave a key to the abbreviations. In B, if you understand geometry, you are a budding mathematician. So we can think of that as an if-then conditional statement. If you understand geometry, then you are a budding mathematician. So in this case, G equals that you understand geometry. M is equaling or representing that you are a budding mathematician. And this double arrow symbol represents if then. So we would read this as if G, then M. And then we have an instance of a conditional. An instance of a conditional is a specific case in which both the antecedent and the consequent of the conditional are true. Now remember at the beginning we said statements individually have to be either true or false, but not both. But because conditional statements are two individual statements, then both could be true. And in that case, it is an instance of a conditional. So example 4 says a geometry student said that this conditional statement is true. If you are a student, then you are taking a geometry course. Is this statement correct? Justify your answer. So in this case, we're just seeing if both the antecedent and consequent are true. So if you are a student, then you are taking a geometry course. Well, that's not necessarily always true. Could be in certain cases, which would be an instance of the conditional, but in most cases, a lot of students aren't taking geometry. So this would be false because you could still be a student who is not in a geometry course. So then we have counterexamples to a conditional. A counterexample to a conditional is a specific case in which the antecedent is true and the consequent is false. So a case where the hypothesis is true, but the conclusion is false. So some counterexamples, we'll look at example 5. They want us to provide a counterexample to prove that the following conditional statement is not true. And in mathematics and in geometry, to prove something is true, we have to prove that it's true in all cases. To prove something's false, we only have to prove it's false in one case, which we consider a counterexample. So, example 5a. If you go outside without an umbrella, then you will get wet. Well, our counterexample would be, if it isn't raining out, then you won't get wet. So, in that case, again, the counterexample, it's a case where the antecedent's true. So, yeah, we still could go outside without an umbrella. That may be true. But the consequent, the conclusion would be false. We're not going to get wet because if it's not raining out, we won't get wet. So in B, if you live in Springfield, then you live in Illinois. Well, we could live in Springfield, but there's many other states that have cities called Springfield. So, our counterexample, there are cities named Springfield that are not in Illinois. Or we could say, you could live in Springfield, but not have to live in Springfield, Illinois. And then part C, if you cannot drive a car, then you are a squirrel. All right, well, there's many creatures and animals who can't drive cars, such as a bird who is not a squirrel. So simply because you cannot drive a car does not necessarily make you a squirrel. And then example 6 is using Venn diagrams to create conditional statements. So in this case, the way to read one of these Venn diagrams would be that everything in the small circle is also part of the larger circle, but not everything in the large circle necessarily is also part of the small circle. So our true statement would be, if it is a squibble, our small circle is squibbles, our large circle is wibbles. So if it is a squibble, then it is a wibble. So every squibble is also a wibble is true. Our false statement, if it is a wibble, then it is a squibble, because there are wibbles out here that are not also squibbles. Now you can disregard or ignore the problems down here. So ignore that part down there. Your problems are posted in Google Classroom as well as on my course schedule. So look there for the accurate page numbers for your class, as well as the correct problem range. But again, the main idea of this lesson is that conditional statements start to lay that foundation or the basis of all our logical mathematical thinking.